Hi there, and welcome to another video in the Physical Geology 101 video series. I'm Geology Professor Shawn Willsey. Thanks for joining me. Today in episode 32, we're going to look at some of the basics that govern a really important process, and that is mass wasting, a process that affects humans all the time in a variety of locations. In our subsequent episode 33, we'll look at the exact types of mass wasting processes that are involved. This Geology 101 video series is modeled after the classes I teach here at the college. No tuition required. It is the same curriculum, the same content that I cover. The only thing you're missing here are some of the field trips and labs, but you can probably supplement a lot of that by looking at some of my other videos. And I'll put some videos in the description that go along with this topic. Okay, so let's go ahead and get started. So mass wasting is often what you would, I guess, commonly call landslides. Although, as we're going to see, there's a lot of different types of ways in which slopes can fail and move, different speeds involved. And so it's a little bit more involved than just calling everything a landslide. So what we're looking at here is the downhill movement of various earth materials due to gravity. Basically, when slopes fail, that's what mass wasting is. We're going to see this can occur in a variety of settings: steep slopes, gentle slopes, dry climates, wet climates. It's an important process in the grand scheme of erosion, of transporting material. And again, it can be fast or slow. There's some that happen almost instantaneously within a few seconds at the most, and some which can take years to sort of culminate. So we got a little eye candy there with a really nasty mass wasting event there in Bolivia in 2011. Let's look at some of the basics here, though, regarding mass wasting. Of course, it's all driven by gravity. And so gravity is this universal constant, and this is what actually causes slopes to fail. Now, looking at it from sort of a physics point of view, if we look at just a block here on an inclined plane on a ramp, we actually have the force of gravity. This red arrow here, this vector, is really just the two components. It is what we call the shear stress, or what we might call the driving force here. So the driving force or the shear force. And then this other force here, the normal force, is the resisting force. And basically, it's a balancing act between the material moving or staying in place, and depending on some of the factors here and how strong these vectors are, that'll sort of dictate whether the slope stays in place or whether it actually moves. We sometimes call the relationship between the shear force and the normal force, or the resisting force, we sometimes call that shear stress or shear strength. So you could sometimes talk about the shear strength of a soil or a slope at any given location. Notice here on these diagrams that as we increase the slope angle from left to right, look what happens to our vectors, to our arrows here. The force of gravity stays the same, but the different forces involved, the shear force or the driving force, becomes longer and more pronounced as the slope angle increases, and the normal force or the resisting force gets shorter as the angle is increased. So there's this constant balancing act here that's going on with any given slope, even though it's every given slope, but even though its angle may not be changing, some of these other factors are changing a little bit. And so to explore that in a little bit more detail, let's head down the hall to the classroom for a little demonstration. We'll do a little quiz along with it and learn more about slope angle and slope stability.
Alrighty, so we've moved down the hallway to the classroom, and we're going to explore this concept of slope angle and the role that water plays in slope stability with a little demonstration here, and also a bit of a quiz for you to handle. So what I have here is an old cookie sheet, and in my beaker here, I have a beaker full of dry, loose sand. And what we're going to do is pour out this dry, loose sand on the cookie sheet. As I do so, I will attempt as best I can to operate the camera and also pour the sand out in a nice, steady, consistent manner and in the same location. So as we do this with the dry, loose sand, what I'd like you to do as part of your little quiz here is to make a prediction about which of these three cross sections you think best demonstrates the pile of sand that I will end up with? Will it look like A, which is a much steeper pile of sand? Will it look like B, a little bit more moderate? Or will that pile of sand look a little bit like C? So those are your three options. So go ahead and think about that and consider it. And then let's go ahead and get right to it. So I'm going to try to do this while operating the camera. So what we're going to do here is pour the sand out. Trying to basically what I'm trying to do here is pour the sand out such that in a nice slow controlled manner, such that I get all the sand grains on top. I'm trying to get every sand grain to go to the tippy top. Now I'm going to pour out a little bit quicker here and a little faster. Just pretend this is like time lapse and sped up a little bit. And what we can see here is if we kind of come and look at it in cross-section view, hopefully you can see that there, it looks a lot like option B on our handout. So with this maybe more moderate angle here, this is maybe a 25, maybe 30 degree angle or so. And I contend that no matter how big the pile of sand is, if I had a dump truck just dropping a bunch of sand in my classroom here, that angle, that cross-sectional angle for the sand would be the same regardless of the size. So that's what dry loose sand looks like. But let's go a little further. Can we get the sand to look anything like A or anything like C? Think about what we might do there. So for A, a lot of times my students are like, hey, you got to add some water to it. And so let's go ahead and do that. Let's grab our beaker of sand here, come over to the sink, get the water going. And there you go, I've added water. This is where the students say, oh no, you got to add more water than that. And luckily for the students, I am an expert. I took a class in water-sand ratios. Just kidding, that's a bit of a lie. And so what I'm doing here is I'm adding sand. We're watching the sand kind of percolate down to the bottom of the beaker. So the water is infiltrating the sand vertically. It's finding the pore space. It's working its way down under the influence of gravity, filling in all the available pore space. What I'm trying to do here is get the sand wet, but not too wet. And we'll look at how that might play a difference here. So it looks like we pretty well just about, might need to tap it a little bit there. Yeah, it looks like all the sand is pretty well wet at this point. And now what I'll try to do, this might be where I need to have three hands here. Let's see if we can get this oriented just right. I might need to pause it here and get this oriented, so hang on. Okay, so I think I've got this situated. We've got our nice pile of dry sand, but what we're trying to do is see if we can make our sand pile up to a much steeper angle. Basically what we saw in A, that very steep pile. So we've added water to the beaker and to the sand here, and so let's see if we can get that here. Ta-da! Oh, is that going to collapse? Hopefully not. So there you have it. There's like a nice little pile of sand. Try to look at it from the side view. Maybe you've done this before, playing with sand as a kid or something like that. And again, this is just like sandcastles, right? So this is the idea that if we have water here, it actually acts as a cohesive agent and it binds and holds the tiny grains of sand together. So we all know making a sandcastle, you're looking for a certain amount of water with the sand in terms of how you mix it. If you have too much water, you might end up not being able to achieve this. But this is like the perfect or pretty close to the perfect ratio of water to sand that allows the sand to maintain a much steeper angle. And so let's see if we can, to kind of round this out, let's see if we can also achieve C here. So what we might do is, let's see here. Let's take our sand, just kind of mash it up here. Let's take the rest of this, get this out. Science is messy. Okay, so there's the rest of our sand. Okay, so we piled up all our sand. I'm going to go ahead and turn this cookie sheet around and actually put it here on a slope. So now I've actually added the cookie sheets at an angle. The water is in the sand, but it's actually acting more as a cohesive glue that's holding the particles together. So then what we'll do to make this fun and engaging for our student audience is we'll pretend this is like a real slope, and we'll put a few little Monopoly houses up on the hill. And now if this is the situation, maybe this is stable for some period of time. But of course, one of the big factors that drives mass wasting is the amount of water in a slope. So we'll go ahead and add some water. So notice as we add water to the slope, no water is coming down the cookie sheet. It's all still being absorbed by the sand. The sand is able to hold that water because there's still available pore space. So let's just keep going with the water up here on the slope. We might add quite a bit of water. There's still quite a bit of available pore space in here. But eventually, at some point, what we're going to see here is at some point we're going to reach a level of saturation. Basically, there is no more pore space for the water to go into. And of course, that's when we see the water pushing aside the sand grains, and now the material is actually flowing and is destabilized. And so we end up with a very low angle of repose. Obviously, I've inclined this on the cookie sheet, but we could have achieved the same thing if I'd kept that cookie sheet level. And now we can say that you can get this kind of geometry to the pile of sand if it's completely saturated. So again, to review, we started with a dry pile of sand with an angle maybe about 25 to 30 degrees. When we added a little bit of water, a certain amount of water, the water was able to bind the particles together, forming a lot of cohesion and allow us to achieve much steeper angles to our pile of sand. But finally, when we added too much water, the water pushed the grains apart, was no longer acting as a cohesive entity, and so it actually separates the grains and creates a very low angle, such as we see here. And now we have a big mess of sand on our cookie sheet there. So pretty sweet stuff. So that's our little classroom demonstration. Let's head back to the lecture.
Okay, so we've learned a little bit through our demonstration about slope angle. Basically, as slopes become steeper, they tend to become more unstable, just as a general rule. The language we use regarding slopes in terms of how steep they can become before material starts to move or slide, that's something we call the angle of repose. And it varies depending on the sediment sizes, also depending on the shape of the grains in that sediment or that soil. And in general, as the size of the particles gets larger, we see that the angle of repose increases a little bit as well. As the sediment or material becomes more angular in terms of its shape, you can also achieve higher angles of repose as well. And that's because those particles have those little angles and sharp corners that can grab and add a little bit more friction. And so if you've ever been past like a sand and gravel plant, you might have seen something like this, a conveyor belt just carrying the aggregate or the sediment up to the top and then getting piled there. And as it piles more and more up on top, eventually it slides or cascades down the side. So if we measure the angle there of that pile, that would give us the angle of repose for that material. Let's look at some other factors that govern slopes as well. We've seen the role of water a little bit, but just to kind of put a fine point on it, we know that a slight amount of water or in sediment will allow it to be cohesive. So water actually acts as a bit of a glue or cohesive material holding the particles together in small quantities. But when we add more water, that water then is forced into the pore spaces between the particles, separating them, and then we lose all our cohesive properties. And the material basically flows. It's no longer able to maintain any sort of structural stability. And so that's what happens when we get too much water in our sediment. Some other effects related to water. Water is heavy. Water adds a lot of weight to the slope, which can be an important factor when we're looking at slope stability. Certain materials like clay actually expand when they're wet, and so they actually can decrease slope stability to some degree. And then depending on the type of rocks you have and some of the chemical properties of the water, we also know, looking at one of our previous episodes on chemical weathering, that you can actually dissolve some rocks as well. And so you can actually cause rocks to chemically weather depending on some of the exact properties there. Some of the other factors that govern slope stability involve vegetation. So vegetation, typically native vegetation, acts as a good slope stability agent. It will keep the water will be absorbed. The canopy of trees and leaves, or the canopy of leaves and branches, will act as a way to dissipate water that's falling out of the sky, so it decreases the erosional energy of that material. Of course, when we lose the vegetation, maybe in a big wildfire or something like that, or maybe just stripping, deforestation, any sort of activity that removes vegetation, we set the stage typically for enhanced slope instability. Now that vegetation is no longer to help with absorbing the water and keeping the slope more stable. And so there's a host of reasons why keeping vegetation on slopes is generally a good idea. But for reasons both natural and sort of human caused, sometimes that's not the case, or at least not possible. Other things that are important are just the types of materials you have, the actual material making up the slope itself. Usually if it's loose material, like loose sediment, it's typically weaker than consolidated material like solid rocks, although you can have fractures in rocks or pre-existing weak layers in rocks like bedding and sedimentary rocks, or foliation, the layering we see in metamorphic rocks. And those structural weaknesses can act to cause the slope to become less stable, even in solid rocks. One of the things here with clay materials, as we've talked about, is it becomes quite, it loses a lot of its shear strength when it can become saturated, and it can flow and cause mass wasting events, kind of like the one shown here. In other places where we have rocks, we might look at actually the orientation of the rocks. Turns out that how those rocks are oriented can play a big role in determining how stable slopes are. We particularly are aware of and a little bit wary of something called a dip slope. So if we have layered rocks, these could either be sedimentary rocks or these could be foliated metamorphic rocks. Even in rocks like granite, you might get fractures running through the rocks. And if any of these planar fabrics like bedding or foliation or fractures is more or less parallel to the slope, that sets up what we call a dip slope. And these are often sites, or can be sites at least, where slope instability occurs and slopes tend to fail. This slope over here to the left of the person is not a dip slope, because the slope angle, which kind of comes off here to the left, is not parallel to the dip of the layers here. But this slope here, kind of shown in this olive green just to the right of the person, is a dip slope. And then we go up the ridge here, but this is not a dip slope. So we'd expect this slope here to potentially be problematic, depending on specific things about the climate, what the rock layers are made out of, and some other factors. But this would be something to be a little bit concerned about if you're ever looking at property or any sort of location that's on a dip slope. And then up here, this is from the Canadian Rockies, but you can see these layers dipping to the right here. So this slope on that side of the mountain would also be a dip slope. And there's a good example of a dip slope failure from northwestern Wyoming, just near Jackson Hole and the Tetons. This happened in 1925, and it's called the Blvd slide. And what we had here geologically was a bed of sandstone sitting over basically a shale. Shales are clay rich. And during a really wet spring, after a heavy snowpack, that's completely saturated the sandstone. So the water percolated down through the sandstone, through those pore spaces. But when it hit that bed of a shale or clay, it was no longer able to move down, because clay is very impermeable. So that water basically saturated that contact between the sandstone and the shale or clay there, caused it to lose a lot of its shear strength, and it slid down. That whole chunk of sandstone on the hillside slid down into the valley, dammed up the Gros Ventre River, and created a lake, the Gros Ventre Lake, which still exists today. So that slide material is still there, damming up the lake. And what that looks like today, you can still see the scar on the mountain, even though that's a good 100 years or so old. You can see the difference in the color of the trees. The old growth trees are darker green. These newer trees that have grown on top of the landslide here are lighter green. But there's the lake, there's the big scar up on the hillside. So we've looked at some of the factors that govern mass wasting, and let's round up this episode by looking at different triggers. What are some things, either natural or human cause, that actually cause slopes to fail? The photo here is actually from 2006. This is down in northern Utah. You can see the damage to the home here. This was when a slope located adjacent to the property became completely saturated, mobilized, moved down the hill, moved out across the flats, ran into the house. The house actually has a basement and window wells, and this slurry of muddy debris went down into the window well, and there was a 4-year-old girl that muddy debris sort of slammed against the wall, and she ended up breaking her femur and having some other minor injuries, just to show you some of the impact and some of the hazards associated with mass wasting. So usually heavy rainfall or snowfall is probably one of the most common triggers, basically adding more water and completely saturating the sediment within a slope. It not only adds the water not only adds weight to the slope, but it reduces the shear strength of that slope. Volcanic eruptions can be part of the equation at times, either erupting and adding ash, or having a volcanic landscape coated in ash, which is very easily mobilized during mass wasting events. So that's part of the equation at times. Earthquakes can cause shaking that can destabilize slopes and cause them to lose their stability and fail and move. And then the last one, the one we've talked about here, of course, is wildfires. Removing that vegetation, removing all the benefits that vegetation produces in enhancing slope stability. Once that's gone, we sometimes see mass wasting events that are pretty rampant in those areas. So these are just some natural triggers, by no means all inclusive, but just some food for thought. Let's turn now to human caused triggers. What are some things that we do in our world on the landscape that can enhance or possibly cause mass wasting events to occur? Well, one thing we do when we build roads, and this isn't universal, but it's pretty common in a lot of locations, is when we have a slope and we need to put a roadway, maybe up and down a canyon or something like that, what we tend to do is we cut into the slope in order to create a level surface for the roadway, and then we take some of that material that's been removed, we dump it over here on the downhill side, and then we compact that material and put the roadway there. And this is a process known as cut and fill. We cut into the slope and we take that fill, that material that's been removed, and we add it here. And don't get me wrong, I'm not saying that these engineering methods or construction methods are 100% doomed to failure. I'm just saying that there's some inherent flaws and there's some things to consider, and we sometimes do see mass wasting events in these locations because these areas have been disturbed in this manner. Notice that locally, by cutting into the slope, we've changed the natural angle of repose. The natural angle of repose came down like this. We just cut into it, creating a steeper angle in this location. The other thing we're not quite sure of, and that can be questionable at times, is how well this removed material now is connected to the underlying material. How, what level of adherence is going on to those two different types of material. So road building and road construction can be a trigger for mass wasting at times. We talked about the removal of native vegetation, maybe not a wildfire though, which by its name implies that it's naturally occurring, but maybe deforestation, clear cutting an area, clearing out a swath of land, maybe for a subdivision or something like that. And we go sometimes and put in grass, or maybe we plant non-native vegetation that demands higher amounts of water. And by doing so, we change the equation and we change some of the dynamics involved with that slope. And when we build buildings, we often use a similar method to this for building construction, cut and fill. So in this case, maybe someone buys some property on a hillside. They want to put their house there. So we cut and remove some portion of the existing slope material. We possibly, rather than trucking that material out, which is costly and you got to have a place to put it, we just keep it on site and put it down here on the downhill portion of the slope. There is the fill, and now we have a little bit bigger pad in which to build our home. And again, don't get me wrong, I'm not saying that every house built like this is doomed to utter failure and collapse. I'm just saying there's some inherent design issues and some considerations to look at when this kind of technique is employed. So some other considerations here as we've with this cut and fill method related to homes or buildings. If we have a situation where the water table is high, maybe as they're cutting down into make the pad here, they intersect the water table and there's a little spring, and maybe the homeowner's excited that it will be, a nice little water feature on their property. But remember, that water table is telling us that everything below that point, all this material down here, is saturated. All the available pore spaces in these rocks or in these sediments is completely filled by water. And so that would be something that I would definitely consider and want to look at in a little bit more detail before I pulled the trigger on either building this home or potentially buying this home. So we've got the steeper cut, we've got the water table, the fill. In this case, I've chosen to give the person a nice little lawn, which will mean that they need to pump water onto the property to grow their grass, most likely, depending on where they are in the world. And that will add more water to the slope and more weight to the slope. The house itself introduces more weight. And so again, these cut and fill methods of construction just need to also involve some engineering considerations or just looking at the slope in a little bit more detail, because every time you do this, you are increasing the risk of some sort of mass wasting event taking place. So that's our episode for this time. In our next episode, we'll look at different mass wasting features. We'll learn to classify mass wasting features based on how they move, what types of material they move, and then we'll do a little quiz to round out that section. But thank you for your support of the channel. Hope you've enjoyed this video and this series, and we'll see you next time. Take care.